I'm Bob Ippolito. I'm going to be talking a little bit about Haskell today in the context of Erlang. So who am I? Well, I'm not classically trained in CS. It seems like many Haskell developers are because they're doing programming language research and they wrote a thesis and they implemented it in Haskell, but that's not me. I've been an Erlang developer for some time. I started in 2006 at Mochi Media, where I wrote our web server and ad server and various other services in Erlang. And I've been a Haskell user since 2012, or maybe more of an enthusiast, because I'm not really doing anything professionally at the moment, let alone Haskell. I'm currently teaching web technologies to teenagers with a nonprofit called Mission Bit. Basically, we teach HTML, CSS, JavaScript, and some back-end stuff as well. We're kind of evolving it at the moment. We're less than a year old. And I'm also doing a bit of advising on the side. So why bother learning Haskell? Well, I learn a lot from studying new languages. I learned a tremendous amount about functional programming from using Erlang and really learning Erlang. But I've also heard over the years that types are supposed to help you write better software. Some of this from Java developers, but some of this also from academics that are using languages like ML or Haskell or even Scala or something like that these days. And I've had a bit of a taste of that. I've used Quick Check and Dialyzer, and I like those tools. And I've also heard that Haskell has good support for parallelism and concurrency. And at the end of the day, it will also help me understand more CS papers, because so many academics are into this Haskell thing. And just to put it in context, this is the RAM footprint per unit of concurrency. So Haskell does quite good here. The minimal amount of concurrency with Haskell, where you have a thread and an mvar. The mvar is just something that you can return a result on, sort of like a promise or a future or a task or an RPC async call or something. So it's about half the size of an Erlang process, 64-bit to 64-bit. And other languages are much worse. So we have it good here. And so how did I start out? Well, for years I was intimidated by Haskell, because at first I didn't understand functional programming, and then other things like all the words, monoid, applicative, functor, all that stuff, it scared me away. But while I briefly worked at Facebook, Brian O'Sullivan taught a class that I could take instead of working during the day, so I did that. And I learned Haskell then, and it was just the catalyst I needed to get started. And after that, I started reading some of the books, and I just deliberately practiced. And one of the ways that I did that was I took the Exercism IO curriculum and I just ported it to Haskell. And I also started reviewing everyone else's Haskell code. So I learned a lot about Haskell by kind of teaching Haskell. And I think I told people the right stuff, but we'll see. And so what's Haskell's appeal? The most interesting thing about Haskell to me is that Haskell has all these abstractions that you can use. Because it's nice to write higher level software, but Haskell has these ways of unraveling it all so that they just go away. So you can write code that's very abstract and very pure and elegant and all that stuff, but you don't pay the cost at runtime. You're not having all those closures actually get created. The compiler is smart enough to inline the right things, and the laziness allows the semantics to work out such that the compiler can just throw away all kinds of stuff, and you can write elegant code that actually works efficiently. And the type system makes maintenance a bit easier because it essentially forces you into Dialyzer every time you compile anything. So if you want to change the type of something over here, it's going to tell you everywhere in your whole program where else you need to refactor. So if you're changing an API or something, you should probably change the type, so it'll tell you all that stuff. And the syntax is pretty nice. Erlang gets some complaints about its syntax. I've grown to love it, but I find Haskell syntax even nicer. And the community is great, because it's like all these super smart people that know math better than I do, and I'm learning math by learning Haskell and computer science, and they're just like really high quality libraries that are very well thought out. Basically, the way that they design libraries is they write like a PhD thesis or a master's thesis or come up with some algebra for how this software should work. And it's very interesting to study that stuff. But there's also very practical libraries too, web servers and byte strings and vectors. So it's a combination of stuff you need and stuff you can learn from. And so the name Haskell comes from this guy, Haskell Curry. So Haskell started off in the 80s. A bunch of PL researchers were all working on like lazy functional programming languages, and they were all doing separate research and had to just re-implement all this stuff all the time. So they decided to form a committee, and they could make a language by committee. And they actually did that. They released the first one on April 1st, but apparently it wasn't a joke because they've been doing it for a very long time. This is some of the original committee. These two faces are kind of familiar. This Philip Wadler guy, he wrote a paper for how you could practically bring subtyping to Erlang. That's not what we ended up with, but it was inspiration, I think, for specs and types and all that stuff. And we have John Hughes of QuickCheck. He was actually involved with the Haskell standard from the beginning, and the first version of QuickCheck was actually in Haskell. And so practically speaking, Haskell more or less started off with the Glasgow Haskell compiler. It's the one that everyone uses today. It started off a long time ago. There's been several revisions to the Haskell standard. It moves more slowly than Erlang syntax. But GHC adds all these extensions all over the place, so you can get cutting-edge features if you really want them. Haskell's domain, it's designed to be a general-purpose language. You can do anything you want in Haskell. It's not necessarily easy to do anything you want in Haskell, but you can really do it. If you really want to, you can make it work. But because it was designed by all these programming language researchers and the tasks that they do all the time is parsing and compilation and type inference, so it's very good at that stuff. It has great libraries for that. And almost every meaningful Haskell program is effectively a domain-specific embedded language. By embedded, I mean it's in Haskell syntax. It's not parsing some string to make that DSL. It actually just is Haskell, but you use it in some more abstract way. But it's not quite so crazy as Lisp because there aren't macros. It's been popular in academia, and it's becoming a little more popular in industry. So these are some of the people that use it. Facebook has some really cool stuff that they've been working on recently, and more boring companies use it. There are some consumer apps. Some of these apps have been sold to Google or Facebook. Other ones are more practical, like the BazQuux is an RSS reader. So for those of you who are using Google's reader, a lot of them have switched over to this one. There's some commercial services like enterprise appointment scheduling and user management, the kind of stuff that Erlang is also good at. And Haskell's bread and butter is really compilers. Like essentially all the Haskell compilers are written in Haskell. GHC, AJHC, the Haskell to JavaScript compilers. Some more researchy programming languages are also implemented in Haskell. Agda and Idris, some compiled to JavaScript languages. And because Haskell is so good at writing compilers, they even made a Perl compiler, the first Perl compiler in Haskell, because it was probably the only thing that they could reasonably implement it in at the time. There's also a number of standalone things. My favorite is Pandoc, which basically takes some markup format and converts it into some other markup format. So I wrote these slides in some abomination of HTML and Markdown, and it made it into this Reveal.js presentation. But it could go LaTeX or PDF or any of that stuff. So distributed revision control, they have some of that stuff. Not too popular these days, but they came up with a nice patch algebra for darks, and it was popular years ago before Git really caught on. A lot of people use this window manager written in Haskell where you can configure it in Haskell. But you don't see like a lot of super popular software here. It's still kind of early days for that use case. So to get Haskell, you get the Haskell Platform. This is essentially like Erlang and OTP, where you have the compiler, the interpreter, and a robust and stable set of packages. Unlike Erlang, these things are all separate. They're managed separately. You can upgrade individual components, all that stuff. It has a tool called Cabal, which is sort of kind of like Rebar, but maybe a little better. And there's a central repository for packages called Hackage. And there's editor support for basically anything you'd use. If you don't want to install anything, there's FP Haskell Center, which is a web-based IDE and cloud deployment platform for Haskell. It's kind of interesting. So Haskell Syntax there's basically two big parts. There's the types and the values, just like in Erlang. And so this is some Erlang syntax that you're pretty familiar with, I would hope, although we're in the Elixir track, so maybe not. So this is the implementation of map from lists.rl. You see that they're deconstructing the list with the head and the tail, and there's this weird runtime check for this function here, just to make sure that you get an error for empty lists. In Haskell, this looks similar, not quite the same, a lot less line noise here, where we check for an empty list, and if so, we return an empty list. Otherwise, we can deconstruct a list. We use an infix colon here rather than the pipe syntax with lists. But otherwise, it's pretty familiar. We have the recursion in the tail. All that stuff is pretty similar, all pattern matching based with multiple heads on the function. So it's not too different. It just has less syntax. But once you start adding types, then Erlang gets a little more unwieldy. I didn't make this up. This is also from lists.rl. This is in OTP, where you have to declare the types for all these variables separately, and it's not inferred, and it's just kind of a mess if you want to add types to everything all the time in Erlang, especially once you have these functions, because functions require a lot of syntax in Erlang for some reason. But if you take this and you translate it into Haskell, it's only one more line rather than 7. So all we have to do is say that a function from A to B, and functions are just an arrow rather than fun with parentheses and all that stuff. And we take a list of A and we return a list of B. And we don't need the runtime check for any of that stuff because the compiler is going to guarantee that a function is passed as the first argument and a list is the second argument, and all the types are homogeneous and everything's good. And it gets even worse once you have even more higher order functions like a fold, like a right fold here. Kind of ugly, but in Erlang, in Haskell, it's relatively simple. It's very easy to see that this is a function of A and B, and it returns a B. The only weird bit here is down here where we have these backticks, and that's just a way to call a function infix, which I'll talk a little bit more about later. I didn't clean this up. This is like actually what Haskell uses for a right fold. And so declaring types, this is the Erlang syntax where you have a sum type, which you declare several possible values. Erlang doesn't allow you to create new types, so you have to embed it in the existing type system. So these are just atoms. But in Haskell, you have very similar syntax. You use data instead of type, and you declare the name of the type and then constructors for that type with pipes to separate them, just like in Erlang. And then if you want a product type, in Erlang, you can't create these, but you can embed it in tuples. In Haskell, you actually create them, although you could embed it in a tuple if you really wanted to, but don't do that. And you also have record syntax, and it's almost as ugly as Erlang's. So this is the record syntax. It will actually define these functions for you, but this is how you would write them, and it's almost as bad as the Erlang. So people hate record syntax in several languages, including Haskell. And you also have abstract data types with recursion. So this is what that looks like in Erlang, if for some reason you want to define your own list type. So you have either an empty list or a cons of a value and then a list. And this is what it looks like in Haskell, so basically the same. The confusing bit at first for me was this difference between types and constructors. Because in Haskell, when you define a type, you're defining something that lives in the type language on the left side of the data here. But on the right side, these constructors, they live in the value language. So here I've highlighted all the type names. So we're defining choice and choices, and we're using the choice type with the choices constructor. And of course, these type annotations are all type language. But the constructors here, definitely, possibly, no way, and choices, are part of the value language. So you're defining it in the type language, but then you use them in the value language, just like code. So you can pattern match on these things, or you can construct instances of those types. And you can annotate any expression with a type if for some reason the inference isn't giving you the right one. You can use these constructors even for higher kinded types, like for a list or an option type or something. You're going to have to construct it with a value, so not just the constructor itself. And you can pattern match just like in Erlang with a case or on a function head. And this is what pattern matching looks like in Erlang. We all know this, hopefully. And it looks similar in Haskell. So this is just telling us whether the constructor is just or it's nothing. And we use the underscore as a wildcard to ignore the value, just like we would in Erlang. And the other thing that I came to realize is that Erlang's pattern matching is really quite powerful. You can do things like this. You can write is equal, where this a variable is bound to more than one place. And what that's actually saying is that these two a's are equal to each other. But you can't do that in Haskell, because equality isn't something that's assumed for all types. So Erlang's pattern matching is more powerful than Haskell because it assumes that every type has this equality constraint, and it's built into pattern matching. Whereas in Haskell, you have to use equality operators in a guard or something to do something equivalent. And another big difference is that in Haskell, you can define your own infix or prefix operators. So the closest thing that Erlang has is that in the Erlang module, you have all the operators available as functions. But it doesn't have user-defined infix operators. You can't write your own function and then use it as an infix operator. But in Haskell, that happens all the time. So you can take infix operators like plus, and you can use them in prefix form by wrapping them in parentheses. Or you can take any arbitrary function and then use it as infix, which is commonly used for like when it would make sense in English, like append or element or something like that. And not only can you define infix anything anywhere, you can also define the precedence and whether it associates to the left or the right, essentially where the parentheses go. And like before, we can see all these higher order things are kind of a mess in Erlang because function syntax. So here we just have two implementations of sum. One of them uses an inline lambda here, and the other one uses a reference to a function. And it's kind of heavy syntax for that. And this is what a very direct translation of that looks like in Haskell. So it's a little less noisy because we don't have all of this fun stuff anywhere. We can just reference add as a value. And here, the lambda syntax is just a backslash, and then the arguments, and then an arrow. But Haskell typically looks even cleaner than that because Haskell only has functions of one argument. There are no functions that have more than one argument. So whenever you write the type signature of something that takes an A and a B and returns a C, what you're really saying is you have a function that takes an A and returns a function from B to C. And then when you're applying a function like f a b, you're really saying f of a and apply b to that. So you can leverage that. And so this is called eta reduction here. So when you have a variable on both sides of an equation, you can just get rid of it because it's exactly the same either way. And so you start doing this, and here we're going to do a little bit of algebra here, converting that infix to prefix, which moves those variables to the end. And then so you end up writing something much simpler in Haskell. You just say plus instead of having to have this function of add to or whatever. You just use the operator wrapped in parentheses. So it just gets a lot shorter once you start doing Haskell-y things to it. And Haskell, of course, also has guards. It's kind of similar to Erlang's, except you use a pipe instead of when. And Haskell has a number of built-in types like Erlang does, but of course you can make your own. Popular type is unit, which is just parentheses. And you use this because you can't have functions of no arguments. So if you have some like void return value or some void argument, you would use unit for that. And you also have a real character type, not integers. And you have doubles and rationals and all sorts of numeric types. And you, of course, also have lists and tuples as well. Like this is the Erlang. And in Haskell, you have this convenient list syntax. You also have the infix operator syntax. And then you can do terrible things with mixing prefix and infix operators, but don't do that. You can also do that with tuples. You have like 10, 4 here as a tuple, but you could write that in prefix syntax as well. And so if you wanted to write a function that makes tuples with 4 as the first element, then you could just pass this in as a function, because this is a function that takes a character and returns a tuple of 4 and that character. And you have strings, but strings by default are like Erlang in that they're just lists, but here they're lists of characters, not lists of integers. And one of the most interesting parts of Haskell is type classes, but it's hard to explain this with an analog to Erlang because Erlang doesn't have anything remotely like type classes. There's modules, but that doesn't quite explain it. And even in Elixir, where you have protocols, these protocols are a global runtime registry. It's not done at compile time, and it's not quite like type classes. And so this is like a very stupid type class to write, and I'm going to show you why you don't have to do this. But if you were to define an is-equal function that would take anything that implements the equals class and tell you whether 2 instances of that class are equal or not. So we have our choice type from before, and we write all this boilerplate. Like we pattern match on the definitely constructor, and if they're both that, then it's true. And then all the other cases, and then if it's anything else, then it's false. And then we can implement this for lists by saying that if A is equal to B, and A's are equal to B's, like the tails are equal, and then if at the end they're 2 empty lists, then lists are equal. But in reality, there's a built-in type class for equality, of course, where you use the equals operator. And you could implement it like this. But that's also stupid because the compiler can just do this for you. So when you define a data type and you want it to support equality, you can just say deriving EQ, and that's it. And it can also automatically derive other type classes for you as well, like ord to implement ordering, so less than, greater than. Enumerations, so if you wanted to make a range of from definitely to no way, you could do that with enumeration. Bounded, you could say that definitely is the minimum bound and no way is the maximum bound. And show and read, which convert to string or from string automatically. And another place where type classes come into play is quick check. So in quick check and Erlang, you have to use all these macros to make it work. So for all and this integer thing. So it's kind of like you're building up a DSL with these macros. But in Haskell, you don't have to write anything special because quick check just uses type classes. So I'm just writing a property which is just a function from integer to Boolean without any quick check boilerplate anywhere to be seen. And it works exactly the same as this. And I can even do this at the command line with a lambda, or at the REPL with a lambda. So I can call quick check with this lambda I, and it takes a list and checks it to make sure if I create a sequence with just that element, if that's the whole list. And this annotation here is just, I'm telling quick check which type I want, because otherwise it would infer unit. And the other big thing, huge difference between Erlang and Haskell is side effects. So in Erlang, execution is strictly from top to bottom, from inside to out, and you can sequence operations with this comma. But in Haskell, you don't do that. You have this do syntax, where you can say, you can bind variables as the result of actions, and you can just execute actions, and then at the end you can return some value. In Scala, this would be called unit. And this would be a for comprehension. But this is all just syntax sugar. So if you have do and then an action, it just desugars to that action. And then you have, if you're binding a variable, then it uses this bind. And then if they're just in sequence, then it uses this, the then operator, which is basically if I had put a wildcard there and ignored it. So you can take things like this, and then you can reduce all of the boilerplate. So here we have this bind here where we're getting the secret variable from the read file action. And if we rewrite that with bind syntax, then we just get this, which isn't too much worse. And we can get rid of the do's entirely. This is entirely desugared here. But then we have this secret variable on both sides of the equation, and we can end up with this, where we're really just piping the output of read file to the input of write file. So you often don't need variables at all when you're coding Haskell. You just sort of chain things together. And this do syntax is more general than just I/O. You can also do it with lists. So here's an example of a list comprehension in Erlang, which is an implementation of flat map. And this is what that looks like with list comprehensions in Haskell. Almost the same, except one pipe instead of two, basically. But we can also write that with do syntax. So you can do slightly more complicated things here, and you can spread it out nicely over multiple lines. And if we start reducing this, then we end up with just piping the list into the function, but we can reduce that even further if we flip it around. And then it turns out that there's an operator just built in that does exactly this. But you would never find this. If you're looking for flat map, you would never find this. So it takes a while to learn what these operators are and how they work. And so Haskell has a great interactive experience. It has run Haskell, which is kind of like eScript. You can just evaluate any Haskell as a script. It has a nice interactive interpreter, or you just boot it up with GHCI, just like typing Erl, except you can quit it with Command D. It has nice interactive features. You can type :T and then any expression, and it will tell you what the type of that expression is, which is awesome for learning Haskell. And there's syntax called Infix Sections, so I can take this plus operator and have 1 on the right side. So I can make a function that adds 1 to the input very simply, and I can see what the type of this is. We can see it takes anything with the num type class, given a list, and returns a list. And I can even see the type of the bind operator here. And you can get even more information with :I. So you can get the information for a type class. I can say, okay, so I have this num type class here. What does it do? And I do :I num, and it'll tell me all of the functions that are implemented by that type class. And it'll also tell me all of the instances. So I know, oh, hey, integer is a num, and int is a num, and float is a num. So if you're trying to learn this stuff, you just kind of play around with it interactively to see what all these implementations are. And of course, if you import other modules, they might also implement these type classes, but these are the built-in ones. And info can also give you information about other things. And the nice thing about it is that it'll tell you where they're defined. So if I want to go look up the implementation of map, I can just go to Google and search for map and find it in ghc.base, or I can search for ghc.base and just find it. And it'll also tell me the fixity of the operator. So if I want to know if I need parentheses or not, it'll tell me. And it'll give me information about types too. So this is some internal garbage for how an integer is represented internally by the compiler. But it'll also tell me all of the type classes that are implemented by int. So I know that ints are bounded, and I can enumerate them, and they have equality, and they're integral, and they're ordered, and all that stuff. And I can load and reload modules dynamically, kind of like you would in Erlang. And I can like execute shell functions and just do all kinds of stuff from the GHCI interpreter. So for a compiled language, it's actually got a really great interactive experience. And here's another example of what I/O looks like and how you can reduce things with Haskell. So this is like an implementation of the WC application. So I'm counting the words in the input. So here I'm just getting all of the input, and then I'm getting the length of the words in that input, and then I'm printing out this integer. And then if I get rid of the do syntax and just convert it to bind with a lambda here, then I get this, but then I can just compose those functions together without any of those intermediate variables. It kind of looks like line noise the first couple times, but this is all just syntax sugar. So this dot is just composing two functions together. Like if you're doing mathematics, it would be like the circle between F and G. That's all it is. And you'll also see $ all over the place when you're reading Haskell code. And the only reason to do a $ is because you don't want to write parentheses, which seems like a ridiculous thing. Like, why would they write $ instead of parentheses? But that's just how they like to do things. They're at war with parentheses. And so another weird thing about Haskell is that it's totally pure. So unlike Erlang, it doesn't just let you do random stuff all over the place. But this purity has benefits because it means that the compiler can just replace anything, reorder operations. It doesn't imply how something has to execute, which turns out to be great for optimizations and equational reasoning. So if I want to do like algebra on my source code, I know that algebra is actually going to work because it's pure. And this is kind of like how GHC looks at source code. So it parses it, and then it renames stuff so that the same variable name isn't reused anywhere. I mean, the same kind of stuff that the Erlang compiler does. Type checks, desugars, and then it has this interesting like optimization feedback loop here where it can optimize the code, and then it looks at it again to see if it can optimize it some more. And it'll do that some predefined number of times or until it hits a fixed point. So it's able to do all these crazy things and make it super fast. And then it'll compile down to LLVM or one of the other backends. And so these are some of the kinds of optimizations that it can do. I'm not going to really talk about that too much. But one of them is super cool. It's sort of like a parse transform. So a rule allows any library, so your own code, you can define your own algebra for how this library should work. So I can say, for example, if I map the result of a map, I really only want to traverse that list once. So I can write a rule that says, instead of mapping a map, just compose the functions together and do one map. And it turns out that they already wrote this rule, and this is kind of why they implemented this pragma to begin with. But it's also used for other stuff. You have this use case with lists, but you also have it with text and byte string and other stuff. So in Haskell, you don't even necessarily need I/O lists because you can just write code that will automatically do the most efficient thing with that input. And the nice thing about it is that it's actually an incentive to write high-level code. Because if I was trying to optimize this by hand, I might not be able to do it. Because this can cross even module boundaries. So this is context sensitive. It's dependent on how you use it. It's not some local optimization that the Erlang compiler can do. This is whole like cross-program optimization. So a simple example is in the byte string library, a common thing to do with strings is to split on some given character, like a new line, for example. So they have this rule that says, if somebody writes code that says break, and break just takes a function, so any arbitrary function that works on given a word 8 or a chair as input. And if it happens to be in this form where they're using the equality operator, then I'm going to rewrite it to this like hand-tuned break byte function. So the user just gets to put arbitrary functions in there, and the library can say, okay, if the function looks like this, then replace it with something faster. So I don't have to have an API that's huge with break on a function, or break on exactly this thing, or break on the range of this thing to this thing. They can just write one of these rules. So an example of that is, so if I wrote break on new lines, then this rule would eventually just turn it into this automatically without me having to do anything or think about optimizations. It allows all the optimization effort to be done in the libraries. You don't have to do it outside in your code. And Haskell is also lazy, which changes basically everything. Instead of like the very strict model where you have to evaluate everything from the inside out, Haskell evaluates everything from the outside in, which takes a while to get used to. But it's interesting because once you're doing things lazily, you don't need special forms for control flow. You want to write your own if, just do it. It just works because you don't have to short circuit because there's nothing to short circuit because nothing evaluates until it needs to be evaluated. It also allows you to do weird things with infinite or cyclic data structures. You can have just infinite lists or functions that operate on infinite lists. You don't have to even think about terminating them because it's context sensitive on how that's going to get evaluated. And it can also skip unused computation. So if, for example, I sort a list, if I want the minimum of a list, I can sort it and get the first element, and that'll execute in linear time. And so the only thing that actually forces evaluation is pattern matching. So here's an example of how Haskell would evaluate a thing. So here I'm printing, I'm going to end up printing the number 2, but I'm doing it in a really weird way. I'm mapping times 2 to all of the integers. And I'm getting the head of that, and then I'm printing it. So then if I start evaluating that outside in, so I have this print statement, or this print action. And so print is just put string line of show of the input. Okay, so I replace that with show. And then the next thing, show needs to evaluate its argument. So I have to evaluate the head, and then head needs to evaluate its argument, the map. And the map needs to evaluate its list argument. And then I have this one ... syntax, which just desugars into this enum from. And then I take this enum from, and I need to evaluate that because map is pattern matching on it to see if it's an empty list or not. So then I evaluate that. Enum from is just n, and then enum from the successor of n. So now I have a list with at least one element in it. And then map evaluates that. So it takes this 1 and multiplies it by 2 and then hits its recursive case. And then I evaluate head. It pattern matches on the list and takes the element, which just is 1 times 2. And then eventually show needs to evaluate that number to figure out how to get the string representation of it. And so it evaluates to 2, and then it shows the string 2. It prints that out. So given like weird, stupid, infinite inputs, it's able to do something sensible here in a relatively small number of steps. And most of this is going to happen at compile time due to inlining. And so these are like what the short circuiting stuff looks like. So the AND operator, it's just case A of true, then B, otherwise false. Right? Like you don't need special forms for any of this stuff. You can just implement them in the language as functions. Pattern matching is really the only primitive here. You can also utilize the laziness to reuse results. Like this is actually a relatively efficient implementation of the Fibonacci sequence by taking the sequence and zipping it with itself. just adding it each way. And it reuses all those computations as it goes. Or if I want to infinitely cycle over some list, I can just implement it as the list appended to the recursive case. And you can iterate, like if I want to define all of the powers of 2, I could iterate with a number of times, or with times 2, and it would just give me all the powers of 2 as a list. And so I can write this elegant code without worrying too much about what the context it'll be used in, because it won't have to evaluate everything, just whatever the context needs. And so the types allow you to enforce constraints at compile time. So here, I'm trying to get the head of true, which isn't a list. So it's going to tell me, OK, so I'm expecting a list, but you gave me a Boolean. So all right. So, and then I type something else. And if I type heads of true, well, that's not even a function that's implemented anywhere. The compiler is actually pretty nice to you. And it says, OK, so there's nothing in scope called heads. But maybe you meant reads or head. It'll actually look for like other functions of similar type with short edit distance. So it's not like Scala or C++ where it'll give you like some crazy error message all the time. It'll actually try and help you. And of course, you can do bad things in the type system because it's Turing complete. Like you can say, let x equals x and x, which defines x in terms of itself, and that just doesn't ever finish computing anything. You can write incomplete pattern matches, and it'll give you exceptions for that, or trying to get the head of an empty list. You can do all sorts of stupid things. It can't totally protect you against yourself. These type classes, there's a lot of built-in ones like functor and equals, which we talked about. Let's see, we'll skip over some of that stuff. And so like the weird words that you hear about all the time, there's monoid and functor and applicative and monad. So monoids are just anything that has an identity and an associative operation. So you could have a type sum, which would, the identity would be 0, because if you add 0 to anything, that's the identity. And the associative operation would be addition. Or you could have product, which you would use multiplication as the associative type. And a super common monoid would be lists. So the identity is the empty list, and the associative operation is appending lists. And then there's functor, which is anything that can be mapped over, which lists are another common example. And applicative is anything that can be mapped over, but you can put the function in the same thing. And monad is just slightly less specific. And these are what those implementations look like. I'm not going to go into it. And you can end up utilizing all these concepts to come up with some pretty cool libraries. Like this is an example of using attoparsec, which is a parser combinator library. So instead of having to write a separate grammar file, you can implement it all in Haskell syntax. So this is a relatively complete parser for most of JSON syntax. So we define a data type with an array, or an object, which is key value pairs, or strings. So it doesn't support numbers, and it doesn't do all the escapes for strings. But I can say that JSON is going to be either parsing text, parsing an object, parsing an array. I can say that string is a double quote followed by many string chunks, and then it's going to end with a double quote. And then a string chunk is either something that's not like characters that are not backslashes, or a single backslash followed by something else, or a double backslash. And then like if I'm parsing an object, I'm looking for the brace, and then I'm looking for pairs separated by comma. And so a pair is just a string and then a colon and then some other JSON object. So it looks like line noise at first, but once you get used to it, you can very quickly build these parsers, and they're all composable. So if I want to just put this in some other grammar, I can just do it, which is hard to do with some other frameworks. And it has foreign function interface, so you can talk to C. It has parallel programming, so if you're doing numerics on big arrays, you can just write the code, and there's efficient libraries that'll run it multi-core. Like this will rotate an image by 180 degrees by permuting the indices of the input matrix, and it'll do it in parallel on multiple cores. And then you also have the concurrency, so you can do that efficiently like Erlang can, because it's less than 2 kilobytes per unit of concurrency here. And so why wouldn't you use Haskell? Well, there's kind of intimidating, all this new terminology, all this stuff. If you're doing things that require a lot of mutable state, that takes some more effort, especially to get used to it. And this laziness is a double-edged sword. So it allows you to write very efficient code, but it also prevents you from reasoning about it without knowing what context it's used in. And once you get used to it, these aren't really so problematic, but it's definitely reasons not to use it. And this is an example of some of the terminology. It's kind of a joke, but not really. A monad is just a monoid in the category of endofunctors. What's the problem? And there's a lot of overloaded words, like return doesn't mean what you think it means. And so, like, this is an example of where laziness can bite you. This may not actually compile to something efficient, even though it looks like it should. And then you would rewrite that to go something like this. And I'm not going to go too much into that. But there's also a lot of nice libraries. You have all of your HTTP servers and templating libraries, all that kind of stuff. Of course, you can't have just one. You need a whole boatload of them. These are just the popular ones. There's, of course, more. There are great tools for publishing and making documentation. So Haddock is kind of like eDoc, except better. There's Diagrams, which allows you to make vector graphics with Haskell code. Haskell, which is like Jekyll, where you can like statically generate a site. Pandoc, which is your markup Swiss Army knife. There's great libraries for parsing. There's good developer tools, like HLint can read your code and give you suggestions for like if you should refactor something. There's these great tools, Hoogle and Hayu, which are search engines. You can actually search by type. So if you're looking for something that takes a string and returns a list of strings, then it'll tell you all of those functions in the standard library. There's even weird things like that you give it a type and then it'll automatically generate code that works with that type. I don't think that's practical, but it's fun. And there's also weird stuff like this title thing, which is a DSL for live coding music patterns. It's kind of fun if you Google for that. And then you have all these parallel distributed libraries. You've got REPA, which is a high-performance Numerix library that runs multi-core. You've got Accelerate, which is almost the same thing, except it runs on the GPU. And you have Cloud Haskell, which is kind of like Erlang, but not quite there yet. And there's great testing tools like QuickCheck, obviously, but also other things like unit testing or program coverage. You have even some like metrics things, and you have got great benchmarking tools that can give you like very statistically accurate information about timing for your code. And if you're interested to learn more, here's a whole bunch of links, but really you should just look at the slides because it'll be easier than trying to write it down. Thank you. Got seconds for questions.
Can you explain page 51 again?
That's 100 pages behind here. So.
Again, other question. What was the practical consequence of Turner refusing to use Miranda as the basis for Haskell?
So the practical consequence was that they had to essentially start from scratch and do it whichever way that they wanted to.
It wasn't open source.
Yeah, Miranda was a commercial product, and Turner didn't want to make it open source. They ended up with a syntax that was very much inspired by Miranda, but they ended up coming to some different conclusions, like type classes were something original with Haskell that were not in Miranda. But if you look at some Miranda code, it's going to look very similar to Haskell.
So looking at an enterprise, future enterprise, where would you put Haskell in your sort of portfolio of tools? As far as when to use, when would it be a good strategic use?
Okay, so when would Haskell be strategically used in enterprise? So in the cases that I've seen it used, it's really sort of at the low platform level, like either as like linting tools or like tools that verify the correctness of your other software, or also just like secret sauce platforms like trading platforms, or Facebook uses it as a spam detection engine that does all these like asynchronous business rule things to talk to all their other systems. So, you know, kind of sort of around the same realms as Erlang, but not so much the systems that run forever and don't stop and need to be hot code loaded. It's not quite there yet, but it's something they're working on. So I wouldn't wholeheartedly recommend that you go use it in enterprise for everything today, but it's definitely a very interesting tool. And if you're doing something like parsing, it can get you a long way really quickly, where some other language, it might have a lot more boilerplate or a lot less flexibility.
How does it benchmark for numerical analysis, where you have a combination of rules and numeric computation?
So how does Haskell's numerics benchmark? So the benchmarking for straight numerics is quite good, like with C level or better. Of course, it depends on which libraries you're using. Some of the libraries for certain kinds of code can do better than other languages. It really depends on the benchmark, and this stuff changes all the time. These things are relatively new to Haskell, like last 8 years or so, and they're just getting to the point to where the benchmarks are something really important to them. So, like any benchmark, on some of them they're going to look great, and others they're not going to look great. So the GPU ones in particular are looking pretty good because you don't have to know as much about how to write good code for a GPU, like with regard to the way that the banks work and the addressing and like having to change the stride and stuff like that. You can do less of that because those rules are built in. Whereas if you were just writing CUDA code, you'd have a hell of a time if you didn't know exactly how the GPU worked.
That's all the time we have for official Q&A. Thanks again, Bob.
Thanks.